two kittens are on a roof. Which one slides off first? The one with the smallest mew. So you've probably seen this kind of problem before. Something is on the side of a hill, it's either accelerating downward or it's stuck on the side of the hill with static friction, and you're trying to figure out how the friction affects the motion of that object. And we are going to study how those problems can be solved. We're not going to solve those in this particular video. We'll have practice problems in a later video. We just want to figure out how that dependence works. So when you have this kind of motion, you first want to figure out what is going to be the most effective coordinate system for you. If you wanted, you could use a standard coordinate system. You could have x go that way and y go that way. But you're going to be making things much harder on yourself, because now when you have motion going down the hill, not only is your velocity going to have an x and a y component, your acceleration is going to have an x and a y component. And technically you could solve that, but you're causing yourself a lot of headaches. And so the strategy is to have the acceleration point down the hill like it's going to be physically, but instead rotate your coordinate system so that the x is aligned along the direction of motion of your object, of your penguin. That way, the acceleration is just in one of your two dimensions. Now, you have good news and bad news, right? The good news is your acceleration's in just one dimension, but your forces are now going to be in different directions in this coordinate system, right? So let's think about the forces that you're going to have acting on your object, right? So the most obvious, of course, is gravity. In our book that we use in this class, we call gravity weight. Sometimes other books use Fg. These are the same force. Weight is just when you're close to the surface of the Earth, it's the force that has the magnitude is equal to m times g. So that's pointing straight down, right? Then you have a normal force that is pointing perpendicular to the surface. And of course, in our case, that's pointing in the y direction. So the normal force, in our book, we use a little n. Other books use F times capital N. We don't have an equation for that force. And now, if you have friction, it's going to be moving backwards relative to the surface. So any friction would be pointing that way. I've mentioned, I think, what I have envisioned in this problem, the penguin is accelerating downhill, so in this case that would be kinetic friction. Like I said, we'll do a full practice problem later. This is just setting us up. Now, this is the physical orientation of this problem. But if we wanted to view it in the orientation of our coordinate system, we could rotate the universe so that it looks like our mathematical coordinate system. Right? And now what we have is that the penguin is just going in the positive x direction. We have the normal forces up, the friction is to the left, but the weight now has a direction that is over to the right as well as downward. So if we have this defined as the angle theta, we need to figure out what the components are. I'm going to leave it to you as a geometry problem to figure out that this is also the angle theta. So if we come over here, this is the angle theta. So if we want to find these components, x and y components of weight, we have wx here and wy here. Right? These are the challenges that I see students face, is how do we know what the wx component of weight is and the wy component? Well, we can do an experiment. We can also do some trigonometry. Let's do the experiment first and see if it confirms the trigonometry.
So how can we measure this? Well, I have a steel bar sitting on the track on a scale. The scale will read the normal force, which has to balance with the y component of the weight, and it's attached to a string which pulls on a force sensor, which has to balance against the x component of the weight. As I lift the track more and more, we can measure each one of these forces and see how it compares.
Here's the recording again with the data being recorded. This is the x component of the weight as the track is being lifted. You can see at that final moment, the data starts going crazy as it gets too high. But up until about 80 degrees, you can see how it compares. When I collect the data for the normal force and the tension, I have to calculate the y component of the weight from the grams by first converting into kilograms and then multiplying by 9.8 meters per second squared. We can see how the normal force and the tension are functions of the angle. And these are the results. The normal force starts at a high value and decreases as the angle continues, and the tension starts at a low value and increases. And you can sort of see how they decrease and increase. Right? This is first curved and then straightens out as it decreases. And this is sort of straight and then begins to curve more and more. So now let's come back to our board and see if that's what we expect. So if we have sine of theta, that's going to be opposite over hypotenuse. The hypotenuse is the long side here, which is equal to the weight, which is equal to mg. The opposite is wx, so we have wx over mg. And so we get wx is equal to mg times sine theta. Similarly, we get that cosine theta is equal to adjacent over hypotenuse, which is wy over mg. So we get that wy is equal to mg cosine theta. And if we go back to our data, that's exactly what we see. We see that the normal force, which is the y component, goes down like a cosine, right? It starts at a high value, and as you get close to 90 degrees, it goes to 0. And the tension, which is the x component, goes up like a sine. It starts at 0 for 0 degrees and goes towards its high value, its peak, its maximum at 90 degrees. So I hope that clears things up. The normal force is going to affect the maximum amount of static friction. It's also going to affect the amount of kinetic friction. And the x component of weight is going to affect the x amount of acceleration, which is what you're going to have in the case of your speedy penguin. All right, thank you. In a while, we will look at some practice problems, but that's going to be another video.